I will speak.
Okay, so welcome back, everyone. So we are glad to have again Alexander Tikhomirov to tell us about his recent work on the moduli of rank 3 sheaves on the projective space with singularities of mixed dimension. Thank you, Alexander.
Thank you very much for this possibility. I will talk about the moduli of rank 3 sheaves on the projective space having mixed dimension of singularities. Let me explain, introduce you into the subject. So, we studied the Gieseker Maruyama moduli space of normalized semistable coherent sheaves of rank 3 with positive second Chern class and integer third Chern class on the projective space. We find the first example of an irreducible component of this moduli space with small values of Chern classes, in which the general sheaf has singularities of mixed dimension. So this means that it has both zero-dimensional and one-dimensional singularities. Of course, one can try to construct a stable or semi-stable sheaf with mixed singularities, but the question is whether it generically deforms into the sheaf again with mixed singularities. That is it a general sheaf or generic sheaf in the certain component of Maruyama scheme? Previously, examples of components of regular of semi-stable sheaves with singularities of mixed dimension were constructed, as you know, only for sheaves of rank 2 in the paper by Ivanov and myself in 18 and by Charles Almeida, Jardim, and myself in 2022. In the last work, we even constructed an infinite series of such moduli components. Now, we want to understand whether such sheaves appear in rank 3 case. This is a joint work by graduate student Irina from High School of Economics. And actually, the paper is just now published. It was published very recently, just this year, in Siberian Mathematical Journal. We can have a reference here, consider reference here. Okay. And this the references to the paper by Ivanov and myself, and to the paper by Jardim and myself. So mostly I will refer to the paper by Ivanov and myself because our construction will concern those modular components which of rank 2 bundles sheaves should be constructed with him. So let me start. By MP3RELM, the Gieseker Maruyama moduli scheme or space of semi-stable coherent rank R sheaves on the projective space P3 of the normalized first Chern class C1 equal E, where E is, as usual, between ranges between minus R plus 1 and 0. And the second Chern class positive, and third Chern class just integer. Please keep in mind that we don't impose the condition that C3 is positive. In rank 3 case, this is not can be not the case. In this, in our paper, we studied the geometry of the modular space MP3 of rank 3, ELM, of sheaves of rank 3. Again, in contrast to the rank 2 case, the geometry of modular sheaves of rank 3 and above on three-dimensional projective varieties is only in the initial stage of development, as you know. In particular, the problem of the existence of reducible components of MP3 ELM, in which general sheaves have singularities of X dimension, remained open by now. So, previously, some examples of components of semistable sheaves with singularities of X dimension, as I said, were constructed for rank 2 case. Sorry. And then, 18, Ivanov and myself found 3 such components in the space, Maruyama space MP3 rank 2, 0, 3, 0. And denoted them, these 3 components were denoted by x21, x10, and x20. Then in 2022, Almeida, Jardim, and myself constructed a Latin series of components, modular components with mixed singularities for general sheaf with increasing second Chern class L. In this talk, we construct the first example of an irreducible component of modular scheme MP3 ELM of rank 3 sheaves. For the value of ELM equal to -2, 3, -6. So you see that third Chern class here is negative. The idea for constructing such sheaves, which we denote by E with subscript script E, psi of rank 3, you'll understand in a moment this notation, which are defined as non-trivial extensions of the form, this is a 3.1. At the left hand, you have the sheaf AP3 minus A, and where A ranges from 1 to 2. And the middle sheaf, just E, and the right-hand sheaf is script E, where script E is a rank 3 sheaves with singularities of mixed dimension belonging to component x21 of the scheme MP3 2.0 mentioned above, which was understood in our paper with Ivanov. Our main result in this work is, which I'm going to talk about, is that the modular scheme MP3 rank 3, -2, 3, -6 has an irreducible component which are denoted by script M bar, in which the general sheaf E is a stable rank 3 sheaf with singularities of X dimension and takes the form just of E subscript E Xi, where Xi is a non-trivial extension of the above type 1. For A equal to, well, the sheaf E, script E is a generic rank 2 sheaf in the component X21 of the Maruyama scheme MP3 rank 2, 0, 3, 0. The singular locus of constructed sheaf capital E is the disjoint union or X of a projective line and the point. The component script M bar is generically reversed and is of dimension 19. So this is our main result. But there are two other main results which have more qualitative nature. First of them is that if we look at the sheaf script E, which enters into our extension at the right-hand side, and take its double dual and look at its singularities, then its singular locus will be a sublocus of the locus, singular locus of script E. So script E again is a sheaf with singularities of one dimension. So the singularities of script E double dual are not preserved when we posted our extension E in the model, where M is just shortened for MP3. Our modulus came as MP3 minus 2, 3, minus 6. In other words, the general sheaf E subscript Xi, in contrast to script E, is locally free at those points where E double dual had singularities. So they disappear when proceed to our extension. That is one effect which we understood. And one more other example, other result is saying that if we take our extension capital E with in the subscript script E and Xi and take its double dual, then it is also stable and locally free now. So that is the present situation. This will be a shift from MP3 of rank 3, minus 2 to 0. Please pay attention to the 0, as it should be for locally free sheaf. The rank 2. Sorry, MP3, there is a misprint, MP3 of rank 2, of rank 2, minus 2 to 0. Okay, so we obtain now the locally free sheaf of rank 3, which is also quite rare situation, and it is stable. So I don't know much construction of locally free rank 2 sheaves. Though now my student Ivanov and Tikhomirov and myself are trying to find such three sheaves of rank 3, which constitute certain components in the Maruyama scheme. Okay, so let me proceed further. Now we will start with the study of singularities of this selected class of rank 3 sheaves, which are given by these extensions. As we noted above, this class consists of non-trivial extensions. So form 1, in which we take for right-hand sheaf script E, generic sheaves in the irreducible components x21, x10, and x20 of the modular space MP3 rank 2 sheaves with Chern classes 0 through 0, which we constructed with Ivanov. That's all these three families, x21, x10, and x20, which each of them is a component of the Maruyama space 2, 0, 0. And we're lucky only with the first one. So the first one, when we take for script E, the sheaf from x2, 1, we will obtain the wanted rank 3 sheaf with singularities as a general sheaf of certain component. For this, to proceed further, we need to describe a certain not open subset of this, each of these components, X and S, where MS belongs to this triple 2, 1, 2, 0, 1, 0. These are the sheaves with singularities from MP3 rank 2, 0, 3, 0, such that their double duals belong to the space R P3, or R means reflexive. So this means that this is component of reflexive sheaves of rank 2 with Chern classes 0, 2 to n. And this E, as it is shown in our paper with Alexei Ivanov, fits into the triple 0 to E to double E, that is a canonical injective morphism, and the kernel is a sheaf just concentrated on a union of line and a point on line L. The sheaf on L will be just sheaf of OL n plus 1 minus S, and W is a point, or in case S equal 1, it is a point. And in case S equals 0, it's just empty set. So, we show there in our paper, I would say, that the singularities of E are the singularities of its double dual, that is the sheaf. Reflexive sheaves, singularities of reflexive sheaf, as you know, are just finite number of points. It is joint union with W and a line. W is a point or an empty set. and we choose them such generically, so that the singularities of reflexive sheaf script EW and the rest of singularities are empty. That is, the W is contained in the singularities of EW. Now L intersects the singularities of EW. The third condition is that also condition of general position is that EW restricted onto L is a triad sheaf. And the last one is that EW, when restricted to a general plane, has sections. That is true because the sheaf EW is a stable reflexive sheaf of M2. And for R, rank 2, and Chern classes 0, 2 to n, we denote a number subset in the Maruyama scheme consisting of reflexive sheaves with and we impose one more condition that they have simple singularities. I will explain a little later what we mean by simple singularities of general position. And these are the results of Han, Chern, and Chang. Okay. Let me remark that all the sheaves from these order subsets X and S star are stable, as we have shown. From now on, we consider the sheaves which are non-trivial extensions of the type 1, where the right-hand sheaf script E belongs to this open subset X of M comma S star. And S also belong to our possible values, and A ranges between 1 and 2. Okay. What is our first result, which we prove? That if capital E is a free sheaf on B3 fitting into this triple number 2, then there are the importance. First, the line and a point, which were singularities of script E, belong also to singularities of E. They don't vanish when you pass to this extension, capital E. And of course, they are included in the union of L line and the point, or W could be empty, of course, and the singularities of the double dual. So it is singularities of E is between these two subsets. Hence, the sheaf E has anyway singularities and means dimension when W is non-empty, because L the short union with W belongs to singularities. And also, we may ask the question, what about the relation between E, capital E, and its double dual? The answer is that the quotient of the canonical injection of E to E double dual is nothing but OL of n plus 1 minus S plus OW. So we have a similar Z sequence to that one in which instead of E you put script E. Okay, so this is trick number 4. I don't want to comment much about the proof. Anyway, it uses the local properties, local X sheaves, and this machinery. Next, consider the sheaf script U from X and S star. Greater enough, is reflexive sheaf. Two n simplest singularities, where simplest simple singularities just means that the sheaf x1 of the pair E double dual comma O or obviously minus A restricted just around the point xk is nothing but the calculator sheaf of the field, the residue field of this point. Therefore, we have the projections. First, we take the sections of the sheaf x1 of EW, comma O minus A, which is just nothing but the sum of its direct summons with supported on x case for k ranging from 1 to 2n. And then take the projection onto each case probably I should put here xk instead of xi. So to one-dimensional space that is k. So the projection of direct sum of residue fields of points to any one of them. And take the compositions from global x1 below double dual O minus A to A0 of x1 of the same pair, which you know is a natural map induced by the spectral sequence of local and global X, and take this projection PRI. And then below by Fi, the composition of these two homomorphisms. So here is the part of one exact sequence arising from the spectral sequence of local and global X, which includes the homomorphism F. Now set consider the open subset in X1 group. Just look at the kernels of each of these Fi and remove the union of these kernels of Fi's. Will show that this subscript E is a dense open subset in X1. This is a technical result, and I also have no time to go into details here. But this is the point, that it is a dense open subset in X1. This means that neither of these projections onto residue fields of points xk is non-zero. That is the point, important point for us. Now, if we look at the sheaf E tilde obtained as a non-zero extension of the type similar to above, but instead of E at the right hand, you take, instead of script E, you take script E double dual. And so our result that if you take now psi as in the union in this open dense subset U subscript E, then it is no periphery at the points of singularities of E double dual. And therefore, it is no periphery everywhere. That is it. So this is how this E tilde will stand for the double dual of our sheaf capital E. So the double dual will eventually be locally sheaf. So, as a consequence of these properties, we obtain theorem, which theorem number 2, under the same assumptions as in theorem 1, the following held. For a generic extension psi in triple 2, namely for psi in this distinguished open subset U script the left inclusion in 3, let me return back for a moment. The left inclusion in theorem 1, you can see this inclusion, the statement, the first statement of theorem 1 says that L W sits in singularities of E, and our result is that it theorem 2 states that it coincides with singularities of E now. So let me return back to here. So the singularities of E is now A union, this is disjoint, of course, union W. In other words, the sheaf E is periphery at the points of singularities of E double dual. Hence, the sheaf capital E double dual, which was denoted above by E tilde, is no periphery. Okay. And this, the second result of theorem 2 is says that it is both sheaves E and E dual are stable in the usual Gieseker sense. To prove this fact, we need to, for rank 3 sheaves, it is technically not so easy as for rank 2 sheaves, but one can pass to the result of Koenig, Schneider, Springer in the textbook, presented in the textbook, where they prove that for rank 3 sheaf which is reflexive. In our case, E double dual is not only reflexive but locally free. So it is applicable to E double dual. When we take a rank 3 reflexive sheaf with first rank class -1 or -2, then it is more stable, and for stability it is enough to check the more stability. It is more stable if the sheaf itself has no sections, and its double dual twisted by -1 also has no sections. and we check this for E first for E double dual, and then the verification is for E itself. Capital E itself is easy. Just use the triple to which they will fit the triple mentioned before. Where E is injected into E double dual, it's a kind of concentrated on a line of the point. And that's it. So it is an easy task. Once you have proved this for E double dual, but for E double dual, it uses essentially the results of Chern and Chang. Okay. We now proceed to a description of the modular family. Script M, A and S of sheaves, where A again ranges between 1 and 2, and S between as above, I mean. Only instead of 6, only I choose here only 5 triples for A and S, which are applicable. For other ones, our computation do not give the result. So we first consider the family T tilde A and S of all such sheaves E subscript E comma psi, satisfying the hypothesis of theorem 2, that is, the pairs of E and of script E and class proportionality of psi, such that E belongs to X and S star. This is an good open subset which we have in X and S, which we have chosen before. And the class of Xi belongs to projectivization of E, that is an open subset in projectivization of X1 group E comma O minus A. Then, as before, the extension which we are looking for belongs to the Maruyama scheme of sheaf of rank 3 with Chern class, first Chern class minus A, that is either -1 or -2, second Chern class 3, and third Chern class minus 3A. And now, of course, the natural morphism, just forget format, nothing else. We send the pair script E, it's asymptotic class, proportionality class of Xi, to the class of E, script E. Now, by our construction, T tilde is dense open subset of a projective bundle over X and S star with fiber Px1 the pair E O minus A. Over another viewpoint. That is followed precisely from the definitions. Projectivization of the open subset of E, U subscript E. X in X1, global X1 group. First, the dimension of T tilde ANS is just the dimension of the base of this vibration, or this dimension of X and S, and the dimension of projectivized dimension of X1 group, which I denote the dimension 0 by small letter X, small symbol X. Now, by theorem 2, which says that each sheaf E, capital E, subscript E, cannot say, is a stable sheaf, will then obtain a modular morphism, well defined, just for sending the pair script I, class of script I plus Xi to the class of the extension E, defined by this pair script E and Xi. Okay, so let M bar A and S be the closure of M in the Maruyama scheme of the image of the set T tilde of the image of phi of the set phi. I guess I list phi of T tilde. So the image under this modular morphism phi of T tilde. That is a very good skill, and let's M without bar M sub A and S be the maximum dense open subset of this closed subset L bar contained in the image, just in the image of T tilde. And let T sub A and S be its the image under phi. Then it follows from the triple extension triple true, one extension triple, that phi sends T, A, and S to M, A, and S, and this is just a composition of an open embedding and a projective boundary over M, A, and S with final projectivized global X1 group, X1 space, or each point of the base M, A, and S. And furthermore, T, by the definition, is a dense open subset in T tilde, together with equality, which I denoted, I guess I denoted it somehow. Yes, by equality star. Please look at this equality of the between the dimensions. So together we have equality star. All this yields the dimension of M is the dimension of X plus dimension of X1 space minus H0 of E of A. Of course, as it should be. Besides, there is an exact triple, which I mentioned in the definition of X and S. Which relates E with E its double dual. When we twist it by 1 minute, we will obtain as a total of the sheaf on L, just OL n plus 2 minus S instead of n plus 1. N plus OW, this is a zero-dimensional sheaf. Twisting by 1 doesn't change it. Okay, so Now, the computations using the above relations and the above tuple, they are quite involved. So I, of course, let's comment on them. Together with all the results of Chern, of the homology of sheaves related to E, I mean to E and its double dual as a reflexive sheaf, Chern did good work for computing the cohomology of tests of E by certain values which are important for us. We obtain the theorem number 3. So under the hypothesis of theorem 2, the families are of the following dimensions. The family of M1 to 1 is 29, of 1 to 0, 27, 110 has dimension 24. The most important for us will be M2 to 1, which has dimension 19. That will be our component, as we will show a little later. And the dimension of the modular family M2 to 0 is 17. And now we're ready to give the final description of the components M, A, and S of the modular space MP3 of rank 3 sheaves with Chern classes -A3 -3A for these admissible triples A and S. As I said before, we just distinguish 5 such triples with A 1 or 2 and NS either 1 or 2, respectively 0 or 1. It is given in the following theorem. This is our last result, which is given here. Varieties M2 to 1 and M2 to 0 are smooth open subsets of irreducible and generically reduced components M bar 2 to 1 and M bar respectively 2 to 0 of the Gieseker modular scheme. MP3 rank 3 and Chern classes -2, 3, -6. Having the dimensions 19 and 17 respectively. The varieties M1 to 1, M1 to 0, and then 1, 1, 0 are of co-dimension at most 1. So at the moment it is not clear whether they are really of co-dimension 1 in the corresponding irreducible components of the modular scheme. Or they are just components. Technically, such things are hard to understand. Sometimes all sheaves E in M2 to 1 and M1 to 1 are stable rank 3 sheaves, and the 3 the singularities of mixed dimension of the form I mixed here. Here L union W, where L is a line and the W is a point. In particular, the general sheaves in the component which we are looking for, script M bar, which is script M bar 2 to 1, has singularities of mixed dimension. The general sheaf in the component M2 to 0 and remaining families are stable rank 3 sheaves with singularities of pure dimension 1 along the line. So of course, M is M bar 2 to 0 is again a component of the Maruyama scheme, but not the sheaf of mixed singularities as a general sheaf in this component. So this is what we understood after checking all these possibilities for constructing our sheaves as extensions. So naturally we found one component M script M bar. In order to prove this term, it is, how to do this in general. We, for analogy a sheaf in M, A, and S, we have to check, to verify the equality of dimensions of M, A, and S and the tangent space to Maruyama scheme. Zariski tangent space at this point E. As we know from the above theorem number 2, the sheaf E is stable, so its dimension is given by a global X1 group of pair E, E. Therefore, by the above equality A, it suffices to verify the equality of dimension of X1 group and dimension of M, A, and S. For our admissible values of A and S. The right-hand side, for the right-hand side of this equality C, we know this dimension as I said in figure 3. I enumerated those dimensions. Observe that since M lies in the modular space, according to the equality B, the description of tangent space, it is enough. So the dimension of M, A, and S doesn't exceed the dimension of tangent space, Zariski tangent space. First, to verify C, it is equivalent to check that the dimension of M is not less than X1 of the pair E. And now the computations, which are very quite involved, show that this inequality is true only for two cases. Which is our case of interest, and 2 to 0, as we said, it also gives a component of Maruyama scheme, but with general sheaf, not with mixed singularities, but only with pure singularities along a line. For the remaining values, there is a lack of 1. I mean, instead of X1 E, comma E does exceed dimension of M, we can only afford that it is not it is reciprocal dimension 1 plus M plus 1. So that means those are the statements of theorem 4. So this is it. I think I gave you the overview of these results. Thank you very much.
Thank you very much, Alexander, for your presentation. Are there any questions?
Of course, you can see that this is our methods are quite traditional and don't involve the modern technique like derived categories because they are not relevant here. Because we are working with small with varieties, varieties with small Chern classes. So concrete geometry is relevant here.
Okay, thank you. Are there any questions? If not, I have some. In this last slide, Alexander, for instance, you put the x1 is smaller than the dimension of the family. Isn't usually the other way around? Right? That the dimension of the family has to be smaller.
Just with opposite, as I said before, an opposite inequality. So to check the real equality, that is equality C, it is enough to check the opposite equality.
Okay. Mm-hmm.
So that is it.
Okay. And also, why do you restrict yourself to these values of n and s? 2, 1, 2, 0, 1, 0?
Before they just arise from those components x21, x20, and x10, which we put for script, the sheaf script here. These are components which we studied with Ivanov. So I just tried to test them, whether they could give as an extension for rank 3 sheaves, as an exceptions of this rank 2 sheaves of these three components. So these are that is the reason why we these numbers trap and one, etc.
So, in principle, if you have other of these X-type components, you can
yes, of course.
you can try
Yes,
to
of
apply.
course. Right, but as you remember, in the classification of rank 2 bundles or rank 2 sheaves with zero third Chern class and second Chern class 3, we could find only 3 of them which have with singularities for general sheaves. Only those 3 which were studied in our paper with Ivanov. All others have seen, of course, could have singularities for and really have. There are at least 10 or something. I don't remember. Maybe you remember better than I. This was, they were enumerated in a paper with, joint paper with Dmitry Markushevich. In all other components, the general sheaf has either it's locally free, these are 2 components, instantons and the next one, and all others have pure singularities of pure dimension. Okay.
Okay, so Anthony has a question as well.
Thanks, Alexander. That was a great talk. That was really interesting. And can I just ask, so in the 3 cases where the dimension of x1 is what seems to be 1 bigger than the dimension of m, is that because it's not smooth at all points?
Yes. It really could be non-smooth. Why not? We cannot exclude this situation, right? But we don't know actually really does this constitute a component as a reduced family? That is it.
You just don't know, right? Okay, fair enough. Thank you.
I can't afford to do that for these components.
Thanks.
More questions, anyone? So if not, I have one more question. So in your theorem 4, you listed various components. Yeah.
Yeah, it is. So there are,
yeah. So in this item 1,
yeah,
Did you
because the good points are smooth points in the
okay.
enzyme.
Did you try to check whether these components intersect?
Oh, that is, very hard business.
Okay.
We should check this for those components of rank 2 sheaves, that components X and S. And only then try to see whether the extensions from rank 2 to rank 3 have intersection. Of course, you ask a very big question, but it is quite hard. I mean, the geometry, when you pass to the generations of sheaves, is quite well.
Okay, thanks. If there are no other questions, so let's thank Alexander again for his presentation.
You can, anyone who wants to see the paper, I mean, which is published now, I can send you a file. Please tell me.
Okay, thank you. I'll stop the recording.